So you are basically doing this y is equal to f of x. Okay, now here this f, we assume that it is a linear function, that is a line. Okay, so we try to fit a straight line through these samples such that the estimated value of y, that is y cap, is very close to actual value. Okay, so this is actual value and this is estimated value. So we try to predict estimated value close to this y. And how we measure the closeness? So we measure the closeness using root mean square error. So we take estimated value, we take original value and just take a difference and square it. So if I do this for all samples, say from I equal to 1 to say capital N, and capital N stands for, suppose, the number of samples available to me, then I put here I and put here I. So we predict individuals y caps and then compare with corresponding actual values, and then we take difference square. Okay, so then we add all together. So this becomes my overall error of the system. And we are designing, or we are placing this line such that this error will be minimum. So we are using differentiation to find out the minima of the squared error. So the squared error, if you see, will be a quadratic function. So there are two types in regression models. One is based on single feature, that is we are just dealing with f of the small x where x is only one dimension and we predict some y. Okay, now when I take this side, I am just doing same thing, but instead of only single variable, I have so many independent variables like this. So there will be a list of variables. So if I do this, then it becomes multivariate. Okay, so this part is multivariate. Then there are two things you can have. One is simple linear function you can fit for the given data. So you're fitting some straight line or you're fitting some plane. Okay, when it goes to multi variate, or it will be called as hyperplane. So when you have only one feature, you're fitting a line. When you have more than one feature, say 2 or 3 or more than that, then this will be plane or hyperplane. So that we are doing. So then we saw some basic regression problems and then classification problems. And this was the derivation for OLS. OLS stands for ordinary least square regression. So like this, we have the squares and we want to minimize the area of this difference square. So this is the actual position of this y at corresponding value of x. Say this is x1 and then this will be y1. This is say x2, then this is corresponding y2, and this is say x3, then it has corresponding y3. Okay, but when I fit a straight line, then for input x1, my prediction is only this.
Hello, sir.
Yes,
Sir, lower side of screen is not visible.
lower side is not visible. Okay, now can you see this thing?
Yes, sir.
Is this fine? Is this fine?
No, sir, not now.
This one?
Yeah, okay, sir.
Okay. So when I put input x1, then corresponding y1 should appear, but instead of that, this term is appearing. So this is my y1 estimated. Okay, so this y1 estimated and y1 has this much difference. So this difference, you can see that if I square it, it becomes this kind of a square. And if I do for all such samples, this area of square, I should adjust this line such that this area of this square should go minimum. So we were seeing this derivation. Let us say I have sample pair x1, y1. For this, I am taking x1 as input, say x1 as input, and y1 as output. But this portion is the estimation, because I am doing this y cap, estimated value of y is equal to beta 0 plus beta 1 x1. So this is my model. This is my regression model. What is unknown in this case is these beta values. I have to fit line. That means I must, as you know, this is mx plus c, simple terms. This is known equation. Instead of that, we are writing here beta 0 plus beta 1 x. So this is nothing but same equation, line equation. So we are not knowing these values, but we want to find out these betas such that I have minimum square error. Okay, so what I do, if I take the y1 sample, then this becomes my estimation, beta 0 plus beta 1 x1 plus error. So there is some error, as we have seen in last image, there is some error, so that is written over here. If I take second sample, then this portion of my equation is y2 estimation. This is y1 estimation and this is y2, and this is the error. This may be plus, this may be minus, but I have to adjust like this. Then if I keep on doing this, then this will be yn estimated. Okay. Now what we saw next was the matrix representation of all these equations, and then we find out the error. So the error estimated is y minus a into beta. So this is the collection of all actual values of y for all the samples. This is that matrix A. Okay, we have seen in last step. This is matrix A. Okay, this collection of x and augmented value 1. So you will see this is 1 added everywhere, so that this multiplication will be done properly and you will get the previous equivalent equations. So we are actually writing all this into simple a matrix form. So this collection of all y's here will be capital Y. Then collection of this x1, x2, xn, and the multiplicand to this is actually 1. Okay, so that will be matrix A, and then you have beta. Beta is collection of this beta 0 and beta 1, then plus your error vector. So error vector will be collection of all this. Okay, so we are just writing same thing in matrix form. That's it. Now target was to minimize the norm of this, or norm square of this error. So norm square of this error vector, if you take norm square, it is even square. The individual values of those error square added together. So that will be my error square. Now, what is my target? My target is to find out values of beta 0 and beta 1 such that this error square is minimized. So I take the help of differentiation. So I differentiate first of all with beta 0 and then I equate this to 0. Okay, this will give me one equation and then I replace this beta 0 by beta 1. It will give me second equation that I will also equate to 0 and then I try to solve beta 0 and beta 1. So if I do like that, I hope you are noting down this derivation. So if there is any doubt, you can ask me. You will get beta 0 like this.
Hello, sir.
Okay. The fact used here is this. The
Hello.
y bar, that is mean value of y for all the given samples, is like this, and x bar is the mean value of x values.
Hello, sir.
So if you take help of this, then you will get beta 0 equal to y bar minus beta 1 into x1 bar. So here still we don't know what is beta 1, we don't know what is beta 0, but how to calculate beta 0? If beta 1 is known, then I can do with the help of equation number 1. Then I differentiate with respect to beta 1, the same error function you can say, and
Yes.
equate to 0. So this will be the step. Then I substitute here value of beta 0 from equation 1 that we have seen just now, and then I simplify. So if I do simplify, then I land to this equation, which is a beta 1 equation. Now next step, we will process this equation further. So in last class we have seen up to this. So today we will process this value of beta 1 further to make it more simplified. Now we are using some fact that summation I y minus y bar bracket, then you multiply it by x bar. Okay, this is looking same as numerator. Instead of xi, I am writing here x bar. Okay, and if I simplify further, I take this x bar inside. So if I take x bar inside, this will be yi into x bar. Summation will remain like this, minus summation again y bar into x bar. Okay, so the terms which are independent of I can take them outside the summation. So this term is independent of I, is taken outside the summation, and this y bar and x bar, they are already independent of I. But when I say sum over I equal to say 1 to n, that means I am adding this number to itself n times. So this will be nothing but n into y bar into x bar. Okay, so this will be n into y bar x bar. Now what will be this? Anybody? So we know that this is y bar. Y bar is the average value of all y's. So I is equal to 1 to n is nothing but addition of all y's, and divided by n will give me mean value. Now here you have just summation of yi's from I equal to 1 to n. So what will be this? This will be, you take this n to this side. So summation I equal to 1 to n yi is nothing but n into y bar. Okay, so you replace this by n into y bar. So this is replaced here. Now what will be total thing? So total thing is x bar into n into y bar minus n into y bar x bar. So this is nothing but n into y bar x bar minus n into y bar x bar. So this is equal to 0 actually. So what is proved here is this quantity this fact in numerator as well as in denominator. So what I do now here is just see carefully what is my trick. Now you see this is my already derived thing. This is already derived thing. I just change this to this. What is change here is I am subtracting, say, this minus x bar. I am just doing this thing. So this bracket I am doing. So this x bar I am adding here intentionally. So what will happen due to this? If you expand this numerator, so this will be summation I yi minus y bar into xi minus summation I yi minus y bar, okay, into x bar. Am I right? So I think this will be this quantity. Okay, this we have already said it is equal to 0. So by adding that term, we are not changing anything. Okay, so by adding this quantity, the equation remains same, since this portion is equal to 0. Okay, so but this will be making the things simplified. So same trick we are going to use in the numerator. So numerator is also added with this minus x bar. So this quantity, if I expand again, will be equal to 0. So advantage of doing this is
Sir,
this.
whole slide is not visible.
Which one?
Sir, complete slide is not visible.
Okay, I will just go out and then come in. Now is it visible?
Yes, sir.
Okay, so only thing is that I cannot comment if I go outside. So let me try to close it and then I will share once again. Okay. Can you see this?
Yes, sir.
Now?
No, sir.
No. Now?
Yes, sir.
Okay, then let it be. So only problem is I cannot write comment now, but we will finish this anyway. So thing is that you will see here this portion, this one is covariance between the two variables y and x. Okay, and the denominator is this portion is variance of x. So these are standard terms, or many packages will support this activity. So that's why we have simplified this. So numerator is covariance and denominator is variance. So covariance is always between two variables, and variance is for a single variable. So this is nothing but your value of the sample minus its mean and square of that. So you will do this for all the samples from I equal to 1 to n, and covariance is the independent variable minus its mean value into dependent variable minus its mean value. You will do this for I equal to 1 to n. So if you add all this, then it will be covariance. Now let us see one example how we do it. Now suppose I have just 5 samples, say like this, and I want to fit a straight line for these 5 samples. So the samples are 1 1, say 2 3, then 4 3, and I think this is 4 3, then 3 2, and then 5 5. Okay, so these are 5 samples. So you will be writing one program in your practicals. So program should look like this. हॅलो, अरे मी क्लासमध्ये तो 5-10 मिनिटांनी करा. So you can note down. You have to write these functions. Say this is a program in Python. So define the function mean value. So mean value will return you mean of the values, that is x and y. So you will call this function maybe 2 times. So what you do, you sum all the values and divide by length of that vector. So this will return you mean. Okay, then you will calculate covariance between x and y. So here we define that function covariance x. So you will supply x, that is the vector which consists of all the values of x. Then you will calculate mean of x from this previous function. Then you will send y and then mean of y. So these 4 quantities will be passed on to this function covariance. So then you will calculate covariance, initialize it to 0, and then for the range, that is from I equal to 1 to n, here length will give you that n value, and you will iterate. So how you will do this repetition is xi minus mean value into yi minus mean value. So whatever we have seen in the form of equations, same thing is implemented. So covariance is returned back. Okay, so this function will return you mean, and this function will return you covariance, and then the variance is required. So variance is just x minus its mean value and square of that. So that will be done for all the values of x. So you will add all these differences square, so that will be variance. So you will require 3 functions like this. Then you will straightway calculate beta values, that is beta 0 and beta 1. So we are having one more function here. So this x will extract the first value from this data set. So we have a data set defined over here at the bottom. So this is the main function. So main function will consist of definition of data set. Here I am just writing 1 1 2 3 4 3 3 2 5 5, these 5 samples, and 1, 2, 4, 3, 5. These are the x values of, so that is x values of my input, and 1, 3, the second number 1, 3, 3, 2, 5, that is y values. So these things are extracted over here. Then we find out x mean and y mean by calling these two functions. So mean is called here with input is x, so it will return me x mean. Then y mean is calculated by passing on the y vector to mean function, so it will return me y mean. So within one step you can find out means of both the variables. Then you know what is b1. So beta 1 is covariance of x and y. So for that you pass on x and mean of x, then you pass on y and mean of y. So divided by variance of x. So you can calculate beta 1 straight away. Okay, so this function will give you beta 1 straight away. Then beta 0, you know, it is just beta 0 is equal to y mean minus beta 1 into x mean. So beta 1 is already computed, you just substitute value and it will return you beta 0. So if you do that, you will get beta 0 and beta, and you can print these values. So if I do that, then for this problem you will get beta 0 equal to I think 0.4 and beta 1 is equal to 0.8, and the fitting of this straight line is like this. Okay, so it's quite good fitting over here for this just 5 samples. Right, now we will extend this concept for multi-dimension or many dimensions. So ALS regression
And the
for,
code, sir.
yes,
Sir, I didn't understand the code.
from where? Starting?
From the definition, from function.
Okay, can you tell me what is this doing? Just see, can you see this code actually?
Yes, sir.
Okay, can you see these two lines?
Yes, sir.
So what it is doing, can you explain? It is defining mean, how to calculate mean. Okay,
And returning the mean.
returning mean. So values will take some values, that is some vector it is expecting. Okay.
Yes, sir.
So x is my collection of all x variables, that is all inputs, and y will be collection of all expected actual values of y. So just we see this previous table. So what is this x? This 1, 2, 4, 3, 5. These are all values of x, and that will go into one vector. And this 1, 3, 3, 2, 5, that will go into another vector, that is y vector. Is that fine?
Yes, sir.
So for input x equal to 1, what I expect is y equal to 1. That is actual value. So I plot this sample here, the first one. Then I expect for input 2, output should be 3. So for 2, you go here, output is 3 here. So this y-axis is y and x-axis is x. So there is nothing new. So 4, if I supply you, then you should return me 3. So if I supply you 4, it should return me 3. Okay. So if I supply you 3, then you should return me 2. If I supply you 5, you should return me 5. So that is what this data is saying. Is that fine? So,
Okay, sir.
but what is done over here is, this is not possible to return you, because I am going to fit a straight line between these, say among these samples like this. I am fitting a straight line like this, such that my prediction for every input, I repeat, prediction for every input will be as close possible to the original one. Now see here, if I put 1 now, I should get 1. But what I am getting here is, if I put here 1, I am getting some 1.4 or so. okay, or maybe 1.2. 1.2, I think. Okay, and you can check with this beta 0 and beta 1. So what beta 0 is? Beta 0 is 0.4 and beta 1 is 0.8. So what is my line equation? Can you tell me?
Y equals to mx plus c.
But using beta 0 and beta 1, can you tell me? What is my model equation is y cap is equal to beta 0 plus beta 1 plus x. Beta 1 into x, right?
Yes, sir.
Now if I put there 0.4 and 0.8 in that equation and put x equal to 1, what is expected, what is estimated value? Can you tell me? Is this visible? Can I write now? Is this visible?
Yes, sir. Visible.
Okay, now see, if it is visible, I can easily tell you. Is this equation, can you see this equation?
Yes.
Okay, now what I am saying is y cap is, what is beta 0? Beta 0 is 0.4, beta 1 is 0.8. This is my actual equation of this line. Agree?
Yes, sir. Yes, sir.
Now if I put x equal to 1, see what happens. If x is equal to 1, this is
1
my
point
1.4. Okay.
1.2.
Sorry, 1.2. So 1.2 is my outcome, but what is expected for input x1? X1 is 1, then y1 is also 1. This is from my training data that is available in my that earlier table, right? But what I am getting due to this line is this much. Agree?
Ah, yes.
Now see second sample. I am expecting 3. Say y2 should be 3 when I supply x2 is equal to 2. But what will be returned to me, I think, is 2. Right? Because of this line. This will be returned. And you can even put here x is equal to 2. So it will be
2.
1.6 plus 0.4. So 2. So this much error is in my prediction. So this much error is in my prediction. Same will be this much error for this sample and this much error for this sample, this much error for this sample. But what is best possible line is this one. I could have fit a line like this. This is also fitting of line for this data, but you will see that these differences, okay, will be more if I fit something else. Okay, so minimum possible error is with this line only. So that is what the concept is. Is this clear?
Oh, yes, sir.
So based on that, we wrote some example. I hope this is visible now. Is this program visible?
Not completely, sir. The lower part is not visible.
Okay, anyway, first for two things.
Yes, sir.
I don't know why it is happening, but anyway. So this function is doing mean calculation. Okay, this function is doing covariance. I will give you this code, don't worry. But you have to write on your own. Just don't copy it. You have to add few lines about plotting the lines after fitting your after calculation of the betas, and then you fit a straight line. I will not give you the code for fitting this line. Okay, you can do that, but rest I will give you. Now instead of just having only one variable, if I have more variables, so here I am extending the concept from say only one variable. So here instead of betas, now I am calling them as thetas. Okay. So when I say beta, it is one dimension. When I call theta, it is many dimension. So here my output is dependent on many variables, say d variables. But my C equation is again linear. So I am assuming again a linear model, and then I am fitting a plane for this. Okay. So if it is multi-dimension, more than say 2 dimension, then I may call it as hyperplane. Or if it is 3 dimension up to three variables or 2 variables, I can say it is a plane. Say like this. Okay. Now again the problem is same. Find out these thetas such that my error, squared error, is minimum. Okay, find out thetas for given data such that the squared error is minimum. So here I am going to do a trick again. I am doing slight adjustment. So this equation on the top, say this one, I can call this as equation 1. I am rewriting in this form. So this theta 0 is suffixed with some x0, which is equal to actually 1. Okay, so this will help me in rewriting the equation in again simple vector forms. So this xi0, where I stands for sample number. So yi estimated, that is the estimation for ith sample, is equal to summation. So hold this equation 1, I am writing in the form of summation. If you expand this equation 2, it will come to equation 1. Only thing is, be careful that I am adding one extra term, which is xi0, and which is always equal to 1, so that I can write in this form. So this will be simplifying the things. If I collect say all y's, if I collect all y's for a given problem, this bar should not be there. So if I collect all y's, estimated kind of a thing, estimation of all y's, then it is equal to x into theta, where x is a matrix which is collection of all the inputs. So this is input 1 actually. This is input 1. Since it has d variables, so it will be actually d plus 1 dimension here. This first dimension we are adding intentionally. Okay, that is always equal to 1, as I said. So anyway, so this is the collection of inputs for first sample. This is collection of inputs for second sample. Earlier it was just one vector. If you remember from last step, I was collecting all the values of x and just putting like this. Okay, now for first sample itself, there will be a list like this. Okay, that will be now a row. So each row here represents the input for expected output y. Okay, now if you take first row and multiply with this column, so that will be y1 estimated. Okay, so first row multiplied by theta vector, So that will give you y1. So if you take second row, say row number 2, and again multiply with theta, it will give you y2 cap. So like that, if you multiply this matrix with this theta vector, you will get here all estimated y's. Okay. So I will take this derivation in next class. I will stop here. As I was informed yesterday that you want to uh, discuss something with me, so I will stop here and I ask your CR to express your problems.
Yes, sir.
Okay, go ahead.
Sir, DSP subject don't have any credits for practical in curriculum, but practical is included.
Now that is modified. The syllabus is modified by the professors, and we have now practicals, because practicals are important for DSP. Somehow they were missed while designing the syllabus, and the respected faculty found out the error later on. Now that is corrected. So
Sir,
syllabus
can
is
you
modified with one practical.
sir, can you share the updated syllabus?
That is the only thing I added, but
Sir,
syllabus is
also
same.
HV.
Syllabus is same. Only practicals are added.
Okay, sir. Sir,